Hello and welcome to InshtantMeshenger. I'm sure you are familiar with many different chat services like Hangouts, iMessage, WhatsApp, Facebook, the list goes on and on. At a very high level, these services consist of your client, so your phone or your computer or whatever, and a centralized application server that actually handles the passing of messages between the clients. However, our chat client is quite different. InshtantMeshenger is a decentralized, mesh-net chat client using peer-to-peer networking, sort of like BitTorrent or Bitcoin. And by decentralized, we mean that unlike those other chat systems, there's no middleman, centralized server required to send your messages to other people. This has several advantages. One of those is reliability. If you're relying on one of those services and they go down or they disappear or something, say goodbye to your chat. In our case, all that is required is an internet protocol network, and that could be just your local area network or it could span the entire globe. It does not matter. There are also some privacy concerns involved when somebody else has control of your data, and this is the case with a lot of these chat services. You don't really know who or what has access to your data, whether it's the company or the government or somebody else. You don't know what they're doing with it. In our design, though, all messages are signed and encrypted using asymmetric cryptography so that nobody else except the intended recipient can read it, and you can always confirm the identity of the sender, which is very nice. So let's get started and take a look at the application. Alright, so InshtantMeshenger was written entirely in C++ and uses Qt for the front end. As you can see here, it's a pretty straightforward and simple GUI, no bells and whistles, but it's very functional. On the left here, we're running some headless nodes on a different network, and these headless nodes use the same libraries, they just don't have the GUI. And these are used to bridge between different networks so we can create large networks of arbitrary topologies with the meshnet. And so these are running right now in a different subnet far away, and if we want, we can actually communicate with these. And what's cool about these, about the program in general, is that it automatically discovers other hosts on your network. So in our debug console over here, when it started up, you can see it sent out discovery probes, and it's trying to find other peers in the network. In this case, nobody else is online here. But if we looked here, when these hosts came online, they found all these peers in the same network that are running in that other subnet. And so now they can all talk to each other automatically. But since we are far away with our chat client, we have to join them manually. So we're going to go into options. Oops, wrong screen. We're going to add a new peer, and this allows us to just specify a new peer that we want to talk to. And it just so happens that this peer we're adding knows about all these other peers. So once we talk to that one peer, it'll give us access to that entire network. So hopefully that worked, and we can now talk to other people on the network. So we got a clear text message over here on these headless nodes. And there's actually another chat client I'm running over there. And you can see it received the messages here. Now, as you notice, these are clear text messages, so anyone can read these. You can't validate who sent them. There's no name even because that you can't verify who sent it. And that's not the main purpose of the application at all. The clear text messages are not really that useful. The main purpose is to share some information, perhaps your public key, to get the conversation started before it's encrypted. So let's say we want to talk to somebody and we want to exchange our keys with them so we can actually encrypt messages to them. First of all, we can go to Options in our Keys menu. We can export a public key and then send it over the network in clear text message. Since it's our public key, it's totally safe to do this. If we go to the other client, they should have received this message as well. And they can add us as a buddy. And usually this is good to do out of band so that you can actually verify the person you're talking to is the one you want to talk to. And we've provided a fingerprint down here to do that with. So the other screen over here where you have your key shows you the fingerprint, and so you could talk out of band, confirm the fingerprints match. So they do in this case B7C1. It looks good. We're going to call this person demo on this side. And you can see here that it added a new buddy to the buddy list and a new tab's opened up here to chat with. But we also have to send this key to the other person so they can encrypt messages the other direction as well. So again, we're going to grab the public key from this one. Oh, got to generate that again. This screen allows you to generate new keys as well as export your current keys for use on a different computer. Alright, so now we got that over here. And again, we check if the fingerprint matches, but we're not going to do that right now because we know it should match. So at this point, we've both added each other as a buddy, and we can now chat using encrypted messages. Alright, so over here in the tab for that buddy, we can see they received that message, and this is fully encrypted. Nobody else can view it. Even though it's propagating to all nodes in the network, no one else can read it because of the cryptography. And same thing other direction. We received their message. That's pretty cool. We can also send encrypted files to our buddies. If we look here on that remote file system in that folder where the binary is and stuff like that, those are the current files that are there right now. Let's say we want to send a file from our local machine. I'm going to grab our project's README file, and that was sent. Also, as a side note, you can see over here these other peers are unable to decrypt these messages because they're encrypted for that one host only. And so we should have sent that file, and if we go to the other chat client, received a file saved as readme.md. So now if we look at that other file system again, we'll see that file has been received successfully. There it is. And so to visualize how this all works, since it's kind of complicated and hard to actually picture how the mesh network's working, we designed a simple web application that collects data from all these nodes and displays it in graphical format. So there's a giant listing of all these packets here that we've been using for testing. If we scroll all the way down, let's send a new packet to show we make a new one here. Oops. Refresh this page, and if we go down again, there's apparently a lot more packets. So if we look at this, we can see a graph of all the nodes talking to each other. And so in this case, we sent it from all the way over here, from the demo to idle to all these nodes. So the fact that we added this node as a peer means we can talk to all of these nodes as well. It's kind of hard to see on here, but you can see that it's showing the connections in breadth first traversal as they happen from the originating node. In this case, it went from idle to all of these nodes located in Amazon EC2 and then propagated throughout various different networks. So as you can see here, let's say our mesh 3 one went offline, this person stopped chatting, they went offline. You could still talk to all these because we have multiple links connected together. So mesh 2 is connected to mesh 1 as well as mesh 3. So if mesh 3 went down, we wouldn't lose mesh 1. Even if mesh 1 went down, we could still talk to Gilliam because there's this link here as well. So it's pretty cool to see how this all comes together and works on a graph. So there's many arbitrary topologies that can result from linking mesh networks and adding a bunch of peers. So it's pretty cool.